Okay, um, why don't we get started? Let me hide the meeting controls and make sure this is on. Nope, there we go. All right, so good morning, happy Friday. The weekend is almost upon us. I'm not sure if you have other classes after this. If so, then I guess I'm what's standing between you and your weekend. It is going to be wickedly cold, especially this evening. I think it's negative degrees, and with the wind chill deeper into the negative degrees. So please make sure you bundle up and don't introduce the opportunity to get sick. Make sure you call your parents too. You might be grown, but as a father, you still want to hear from your kids. All right. That being the case, today hopefully, I'll remember everything I had to say. I have a little bit of sore throat and sniffles, so I apologize ahead of time for that. So hopefully, I'll remember everything I intended to say. But today, we'll pick up with the balance of where we left off concerning multivariate distributions, and we'll comment about so-called joint distributions in the next module, talk a little bit about marginalization and one of the several methods that you can use to measure what I've been calling variable coupling. Okay, but before we begin, the usual administrative stuff. The reading has changed, and this is by the 7th of February, and it's all APIs related to visualization for PyPlot, which is the submodule in the Matplotlib visualization library. All of these are curated for you in the course resources section on the course Moodle site, and you're not limited to these. Certainly, this stuff is popular enough that you're going to see very many different sites out there containing explanations for them. I personally like the documentation of record, but that's not the only source that's out there. Project number 2 on visualization for the SMB spaghetti meatballs broccoli problem we've been carrying forward is due Tuesday, this Tuesday, the 7th of February, at the usual 1 second before midnight. If you've done it already, please go ahead. Don't wait and submit it. Then do your happy dance like the cat up here, whatever you choose to do. But please make sure that when you make your archive, that you are including all of the components that are required for submission. So please make sure you double check that. And one way to do so is to take your archive file, unzip it, and then verify that what is inside the zip file is actually coincides with everything that needs to be handed in. And so for this, you're going to be handing in the IPython file. That's IPYNB, and that's not the same as doing a file save as in your browser when it brings up the Jupyter Notebook. You're going to look on your file system, and in that location where you start Jupyter Lab, that's where it places the IPYNB file. That's your notebook. Okay, any questions? No questions? No? And today, if memory serves me, I think we're also going to talk about visualizations. Yes, the visualization types. That's what I forgot. So why don't we jump right in? Where we last left off, we talked about this idea of objects in the world being described with multiple variables. And so that's the case that you really find with objects in the real world. We talked about singular random variables and their distributions, but when we think of these random variables as measurements with this framework, we can have many different measurements over the same raw observation, where those observations are objects of some sort. And so we said this connects things to the real world, especially as it pertains to experimentation and sensors and stuff like that. And so here we had a population of dogs. I think it was a yellow lab or golden retriever. I always confuse the two breeds. And we have a bunch of attributes, length, width, height, mass, and coat, that collectively describe a particular breed of dog. And we said that instantiations of these variables, you can have many different types of instantiations, but it's the particular co-occurrence of certain values for these random variables that describe what it means to be a yellow lab different from, say, a German Shepherd. Okay. Any questions about this? No questions? To jar your memories from Monday? All right. And so we said that there's this relationship. We have out there all of the quantities or objects of interest, our population, and these values associated or attributes associated with these objects collectively comprising your population, these parameters defining the distributions that give you these objects, they're hidden from you. You don't have access to them. But what you do have is the ability to draw from instances within that population, i.e. your samples. And then from your samples, you compute functions over them, our so-called statistics. And if you do it right, for some definition of right, these statistics will coincide perfectly with these unknown parameters, these unknowns, ground truths about the population. And so what can we do with these statistics? Well, we can mimic our unknown distribution, defining the objects you get from the population. And if you can mimic them, now you can sample from them, producing artificial individuals. And then you can ask questions of those artificial individuals, our so-called inference. Okay. Any questions? No questions? Jar your memories? Yeah. All right. Okay. So let's continue on with this idea of sampling. And sampling, by its very nature, you're selecting a subset of that population. In some cases, like the homeless population, you can sort of hypothesize about the structure of this population and use this idea of time and location to try to seek out these various pockets or these cohorts that you believe comprise your population. But in other cases, when you sample, you have no control over it. They're just given to you, and you have to take what your population distribution gives you. And so because you're using a subset, or you're getting or dealing with a subset of these objects in the population, by that very nature, from one round of sampling to the next, these attributes, these instantiations, vector valued, representing the individual objects or the n many measurements, your random vector, they can be different from one round to the next. And so because you're using this subset, well, each sample can be off from this population, this idea of typical, right? And so because of that, you can have error. And said error is called sampling error. And one of the things you try to mitigate when you're designing your experiment that gives you your samples is you're trying to reduce this so-called sampling error. Because the more you reduce it, and there are ways of doing this, the closer and closer your estimator, your sample statistic, coincides with your population. And we'll have an exercise where we'll actually see that happening. And so for so-called sampling errors, most error in your statistics can be mitigated by increasing the sample size. Now, in many of the proofs, you see in the limit as n approaches infinity, but in the practical implementation, n doesn't really approach infinity because you have finite resources and you have to decide judiciously where you place your samples, all right? And so that being the case more generally, as your sample size increases and goes to infinity, your so-called sampling error gets smaller and smaller and smaller. And depending on the complexity of that distribution, you're going to need a larger n, right? Sometimes you can get away with a small n. Okay. Any questions about this? No? Make sense? And so then you have this other thing, non-sampling error. And for non-sampling error, that arises because of flaws in your experimental design. And for non-sampling error, there's no amount of samples, and goes to infinity, that can decrease this type of sampling error. And what you do to change this or decrease or mitigate non-sampling error is to change your experiment. And so it's really, really important to carefully design your experiments with an eye towards potential sampling errors. You can't fix it as n goes to infinity. You can't decrease non-sampling error. Okay, so some concrete examples, and these aren't the only types of non-sampling errors. And these are my own names, and I choose these names because they're descriptive. But one is the wrong population. Suppose you were to conduct a survey. In your survey, you selected 100 Samsung Galaxy users, a brand of cell phone, um, and on campus, and you asked them, what's your favorite new feature on the iPhone? That's a non-sampling error. Okay. Suppose this one, dependent observations. You were to ask students in computer science if the bookstore has good prices. Okay? That's a non-sampling error. And I'll explain why. This next one, not the equal likely selection. This idea of equally likely selection of members of the population is really important if you want your statistics to be representative of the population. And an example of that, you randomly sample flyers on different flights. And let's say you choose flights without preference, and on each flight you sample 10 passengers. And we'll talk a little bit about why that has non-sampling error. And then this idea of bias, you conduct perhaps a phone poll about grocery items that are frequently purchased, but you do that using landlines. That's a type of non-sampling error. And so here, well, the first one, those users on the Samsung Galaxy, they have limited experience with the iPhone. Maybe they had an iPhone a long time ago and they're not as conversant with all the things that iPhone products can do. So there you've selected the wrong cohort in your population from which to sample. And because their experience is limited, well, the results you get are not going to be representative, especially of the population or the cohort of interest for this particular example. Any questions? And so there you have to go back to your experimental protocol and redesign your protocol. No amount of samples, if you were to say, okay, instead of 100 Samsung Galaxy users, I'll sample 1,000. That'll make it better. That's not going to make it better because there's a flaw in the experimental design. That's a non-sampling error. Computer science students about the bookstore, well, they're in the same major and they are in the same classes for the most part. And so they're going to talk to one another. And because they talk to one another, they share information and they're going to influence their decisions. Hey, I found this book for DS125 cheaper on Abe Books. I found it cheaper on Amazon. And because of this non-independence or freestanding decision among students that communicate with one another, you're not going to have this idea of no particular preference for the cohort of students that you sample. Another one for the flights, well, if you select a flight and pick without preference 10 passengers, you're going to be more representing the frequent flyers. By their very definition, they fly a lot. Perhaps it's business travelers or just folks who commute by airplane. I know people like that who commute by airplane for work from Boston to New York. And that being the case, you're going to miss those perhaps family vacationers. They might take 1 or 2 flights a year, and they're pretty big trips. And so if, in particular, your study was about vacation for certain cohorts of the population, by your experiments, by this scheme, you're going to miss that segment of the population because you're going to be representing frequent flyers and not, in particular, the cohort of interest. And then lastly, phone poll. Those households that are cell phone only tend to be younger, right? And so your representation for anything you talk about, collect about grocery behavior, grocery shopping behavior, is going to be more representative of, in general, an older audience. And so if you're targeting, for example, college-aged young people, 18 to 24, you're going to miss out on them for the most part because they tend to be cell phone only households, loosely defined as household. Could be a set of housemates and could be independent student, stuff like that. Okay, any questions? Does that make sense? And so that just says when you sample, it's really important to consider how you design your samples because these types of errors, so-called non-sampling errors, you can't fix by increasing your sample size. Okay, any questions? No questions? All right. So the goal then, generally for sampling, is to draw examples from or objects from the population randomly without preference. Now, this idea of randomly, you might have to, by design, in the case of the homeless population, make a concerted effort to place your samples in different locations and at different times. You can't just encounter a homeless person and encounter or contact all of the different segments of that population. You're going to miss out. So sometimes this idea of random, i.e., without preference, requires deliberate effort to try to spread out your samples or spend them in various locations. The examples you collect are collected independently. What that means is that one draw from the population, depending on those outcomes you measure, you can't use those outcomes to decide where you sample next, okay? Because then you introduce a dependence. They have to be independent and equally likely to be selected. You just choose what you get without pre-filtering, because that will alter the statistics that you're enterprising to calculate. And they have to be representative, lastly, of the underlying population. Any questions? That makes sense? Yeah. So we'll have an exercise concerning survey design to kind of round out all the topics of interest for this class. Now, certainly, there are only some things that we can do in this class. To do this for real, it might take you a whole semester just to design and execute the survey and calculate the results. Question? Mm-hmm. Mm-hmm. Yes. Well, off the top of my head, let's say if you wanted to know, for example, the average age of a Clark student, right? If you only sample two Clark students in the morning, you might just get two people who are freshmen, right? Because the first year courses tend to be earlier in the morning. But if you decided you were going to gather, for example, 500 samples, the time it takes you to get 500 samples, as you increase that number, you're going to more likely encounter individuals that are juniors, that are seniors, that are grad students, and so forth. And so we'll actually have a project where you see this occur for yourself. But in absence of this implicit bias that you see here, when I say implicit bias, I mean the statistical definition, not the social definition. If there's no bias inherent in how you draw your samples or no preference, then in the limit, as you increase the sample size, it gets smaller and smaller and smaller. Mathematically, you see that by the variance going to zero. If you let n go to infinity, because you have 1 over n in the expression, it goes to zero. And a variance of zero means your distribution has all the probability over 1 point, and that's over the mean. Okay. Did I answer your question? Okay. So we'll get to more of those nuanced details in the next coming weeks in the semester. All right, any other questions? Let me make sure my headset is still connected, because if I go out of range, it drops the connection and the sound gets harder on the recording. Okay. And so let's talk about so-called descriptive statistics. And this idea of a probabilistic average, its whole purpose is to summarize or describe something about the population. And yes, you want the statistic to be representative of the unknown attribute for the population. But nonetheless, we still use these statistics to tell us things like the center of the distribution, or the central behavior, or the dispersion that among the measurements that you're going to take. And so as a probability, it's a proportion per centum, and it varies on the real number line on the closed interval between 0 and 1. So you can have a probability of 0, probability of 1, probability of anything in between as a real number. Now, as a vector valued quantity, when we talk about these types of probabilities, we're talking about the probability of the instantiation of all of the variables together as they co-occur. So if we had, for example, that top row, these measurements, including the categorical as well as quantitative variables, that has a probability. Let's say that had a probability of 0.05, 5%. That would be 5% of the time we're going to see that instantiation across all of our variable outcomes in the random vector. It's not for the multivariate case over a single variable. That probability is defined over the co-occurrence of the instantiations across the vector. Okay. Any questions about this? Does that make sense? Yeah. And so we get our probability, and like we talked about in the single variate case, when can I see you again? It describes how often you see this particular instantiation or outcome across our vector instantiations of random variables relative to all the other possible outcomes. Now, of course, as you can imagine, is you increase the rank or the number of random variables in our vector, any particular instantiation might have a very small probability because it gets really, really big, all the possibilities really, really fast. It's multiplicative. And so here, when we talk about this distribution or this type of probability over a random vector, a so-called joint probability, we refer to it over the entire instantiation. But we can still traffic in a single variable, a so-called marginal distribution. And so here, I could certainly enterprise to compute a histogram over a single column, a single variable's outcomes. That is not mathematically correct. If you do it, it'll tell you something, but the reason it's not mathematically correct, because, for example, anytime I see, for example, 38.5 for the length variable, associated with that particular outcome of that particular variable are all the other possible combinations of width, height, mass, and code. And so if you correctly wanted to compute the probability of a single variable, you have to add up all of the instantiations of everything else for that particular value. And that's a process called marginalization, and we'll talk about that more formally. So this reason for this is that a probability, and we'll define on Monday more rigorously what a probability is mathematically, but a probability has to sum to 1 over all of the instantiations. And so that means this instantiation, you add up all those, and that's the probability for length is 38.5. And then for all the places where you see length is 42, you have to add up all of those probabilities, and you have to do that for each outcome of that length variable. And so if you did the histogram, as it's listed here for this highlight, it'll give you a histogram, but that's not mathematically correct because that's not formally a probability. Okay? All right. And so because you have these instantiations, it's not enough for a single variable within a random vector to just show its distribution and say, hey, let me give you some summaries about the behavior of this variable. Because it's coupled to other things, you have to include that consideration in your calculation. Any questions? No? All right. And so probabilities have central values. We talked about the mean, and that's considered the center of the distribution. That's the average or expected behavior, one of the probabilistic averages we talked about. They also have a variance, the square root of which is a standard deviation, and that's the measure of the dispersion, how spread out over the support set this probability mass is. Any questions? Does that make sense? All right. And so if our standard deviation is smaller, that means our values that occur more frequently is a smaller part of our subset, right? Is a smaller part of our support set, I should say. Said differently, that means very few of your trial outcomes, you're going to see values out here for the red version. For the blue version, more of your outcomes out here and over here, you're going to see for the blue version. And so this dispersion is really, really important. It tells you this idea of how you could call it wiggly your values are for the random variable of interest. You can use this to your benefit in fields like finance. In other fields like human services, you then enterprise, why is this variability so high? And that you could use that sort of information to say, well, it varies a lot for that measurement. So let me go ahead and redesign my experiment. Maybe I need to subdivide my population because I'm getting so much variability. Okay. Any questions about this? Make sense? Okay. And so we talked about the mean, we talked about the variance, but there are other measures, such as the median and the quartiles, that tell you things about the spread or dispersion of the distribution. You can use them for that. And the reason we'll talk about probably on Monday or next week, Friday, has to do with this idea of robustness, sensitivity to extreme values or outliers. Okay. Any questions? No? All right. And so we have all of these measures that we can use to summarize the aboutness or the behavior of the values output or returned by a random variable. Okay, so the bad news, there's good news and bad news. The bad news is you don't have access to the parameters of the governing population distribution, the so-called population parameters. But the good news is you can compute reasonable replacements from samples, and these replacements are functions or statistics. And as long as they are quote unquote stable, and we'll talk about what stable means, they'll make reasonable replacements that you can then safely assume apply well to this unknown population. Any questions? No? All right, so what are these stability criteria? Well, it has to do with two things, biasness and consistency. And so if you have an estimator or statistic and it passes these tests, is it unbiased and is it consistent? Then yes, it makes a reasonable replacement. Now, mathematically, if you put together a statistic and you find it doesn't pass these tests, you have to transform that statistic until it does pass that test. And there are ways of doing this. And so an estimator, theta hat, that's just another name for a statistic that you're enterprising to use as a replacement for an unknown parameter theta. For example, in the homeless population, do you know what the average age is of a member of the homeless population? Ground truth, I don't know. You have to get enough samples and compute your average until it becomes stable. Okay, and so an estimator, theta hat, is a statistic you're enterprising to use as a replacement for some unknown parameter theta. And this estimator theta hat is so-called unbiased if its expectation, E of theta hat, is equal to theta. What does that mean practically? It means that if you compute, for example, the average, it's going to be one value. You take another set of samples, compute the average, it's going to be a little bit different. But you compute that average some number of times and then compute the average of the average, well, that will equal exactly, precisely, within very small error, the overall average in the population. And so here we say, if the expectation, the probabilistic average for each statistic's value is equal to the unknown parameter, then it is so-called unbiased. That means on average, it gives you exactly what you're looking for. And so here we have a statistic, X bar, the average or the so-called sample mean. You take little n many samples, x1 through xn, big X1 through big Xn, so it's n many random variables, and you divide by n. This gives you exactly mu, which is the population mean. Okay? All right. Now, in a standard stats course, problem stats course, you'd actually prove it mathematically, but we're not going to prove that mathematically here. Okay, any questions about this? But we will have an empirical exercise on one of the projects where you'll actually see this work, right? I'll give you the population parameter because you need to compare it to see, oh, is it getting closer and closer as you increase your sample size? Okay. The other litmus test, consistency, it says, is that me? Oh, okay. That's the same bell I used to wake up. So they kind of gave me a flashback from 6 a.m. this morning. The other one is consistency. It says that as you increase your sample size n, the probability that your estimator statistic, theta hat, will be different from the ground truth population parameter theta. That'll be different by some error epsilon. That probability is going to go to 0 as you increase the sample size. Now, The rate at which it gets theta hat gets closer and closer and closer to theta, that depends on the complexity of your distribution, right? And there are various ways people think about that. And so what it says is that if you want your statistic to be very, very close, epsilon, to the unknown, just increase your sample size. So here we have two criteria to your question about increasing the sample size. If you increase the sample size, it'll get closer and closer and closer, so the variability will be smaller. And if you do it several times, on average, it's going to be spot on to this unknown. And so we can use that in various ways for practical problems. Okay. Any questions? And we could also prove consistency mathematically, but we won't do it in this class. Yes, question. Mm-hmm. It is a guess, but this idea of best guess, you can prove it theoretically through proof, and then empirically, this idea of the schedule of how you increase n, it really depends on how complex the probability is. Because if you have a probability, and thank you for asking that, let's say you have a probability that looks like this. All right, well, if you increase n, you're gonna get very close to this distribution, right? But let's say you have another probability distribution that looks like this. If you only have a small number of samples, let's say you had 3 samples. Well, and let's say this were ground truth. Because this is ground truth, and you don't get to see it, I'm just showing it to you, right? Well, here we have some peaks in the probability mass. And because there are peaks in the probability mass, by definition, the values in this range, in this range, and this range are going to be more numerous. Because by definition, higher probability mass means it's going to occur when can I see you again more frequently. So if you sampled 3 times, okay, you might get some value somewhere in here, say somewhere in here, and maybe somewhere in here. Okay, if n, your sample size is 3, you're going to have some representation here, but you're missing out on a lot of parts of the distribution. So for a complex distribution like this, when you sample a lot of times, let's say 1,000 times, you're going to get a concentration in here, maybe something here, and then a higher concentration where you have peaks. And so you need a large sample size, a much larger sample size in this case, because you have to fill in more of the details of this distribution in all the very many places where it places probability mass. But for something like this, it's smooth, it increases, you get a lot of mass in this region and a little bit here. Does that make sense? And so when you increase this complexity, you kind of have to ask it more, where are you placing mass? And that's effectively what you're doing when you sample. And so because there's mass in many more different places across your support set, you need to ask it for more information versus here. Okay. And any other questions? That makes sense? Okay. And so let's see. If you have a statistic as an estimator is nothing more than a statistic that you're enterprising to use as a replacement for the unknown population parameter. And if your estimator passes these 2 tests, unbiased and consistent, you know that it will be a good replacement. Okay, all right. Any other questions? No? All right. And so that's consistent. So the sample mean, which is noted as X bar, is one such statistic. It passes the unbiased test and it passes the consistency test. Now, when we talk about parameter estimation, method of moments parameter estimation, and max likelihood estimation, we'll arrive upon this X bar, our sample mean, more precisely. Okay, but this idea of the arithmetic average or the sample mean, it is a stable statistic. and it's therefore a reasonable replacement for the unknown population mean mu. Okay. Any questions? That makes sense? And we can actually prove that mathematically. Maybe I'll do that in another class meeting. All right. And so the variance, when we take the variance, this is not a typo. You'll notice in this expression for s squared, we have a sample, n many wide. So x1 is the first sample, x2 is the second sample, x3, and so forth, up to n many samples. You'll notice in this expression, s squared is a stable statistic and therefore a reasonable replacement for the unknown population parameter, sigma squared, the variance. And therefore, the square root of s squared, or s, is also a reasonable replacement for standard deviation for the population distribution, which is sigma, standard deviation. Now, in the expression for s squared, you'll see this leading coefficient, 1 upon quantity n minus 1. That's not a typo. If you were to use 1 upon n, that's a biased estimate. It doesn't pass this litmus test of being unbiased. It fails. And so what did someone do? They said, okay, how do we fix up this 1 upon n expression to make sure that it is unbiased? And you change this coefficient to 1 upon n. Okay. And so here we have 1 upon n, and then we have in our sum the value of the random variable xi minus the sample mean x bar quantity squared. And this is all from data, the sample version of the estimator for sigma squared or sigma squared hat. Any questions? Does that make sense? Yes. Why is it biased? If you do the proof for unbiased, the expectation of the statistic, you do not get sigma squared. And we can do that in another class meeting, or maybe I'll put it on a recording and post it on Canvas. But it fails the unbiased part of that test, unbiased and consistent. Okay. Any questions, other questions? No? All right. So let's switch to the other slide deck. And we will spend the rest of today, stop the share, reshare. That's 5. Let me first do this. Let's exit this. Oh, what just happened? Go back to Zoom. Still there. That's 5. Let's go screen show and slide view. So that I can see what you're seeing. Let me make sure I'm still recording. Still recording. Let me hide the meeting controls. And okay. So why don't we continue on? And so here we're going to focus on, I think it's visualization, and we'll talk about so-called joint distributions. And so the administrative stuff hasn't changed. Last time on Monday, we talked about populations, we talked about sampling, and this idea of selection without preference from among the objects under consideration. And so I use this idea of a hierarchical population to really ground out visually this idea of this notion of with equal preference. And so here, when we sample, we don't want to make sure that we're not preferring, for example, the cohort of veterans over, say, the cohort of those who struggle in the homeless population with drug addiction. And so how that would play out in practice is you have to know where the homeless congregate, where they can be found, and what times they can be found, and then spread out your samples, spend your samples in an equal way among all those different locales. And that takes some study. So then we talked about this idea of measuring functions over the data. And our whole purpose in talking about random variables was connect together mathematically the theory with how you might implement this. And so we said that you can use these statistics, so-called estimators, as replacements for the unknown ground truth quantities floating out there in the population that you don't have access to. Any questions? No? Yes. That's a great question. I had them non-overlapping, and that's not what jibes in real life. If you have multiple categories, that's called a mixture distribution. It's a totally different model for how you do it. Now, if they match multiple categories, in practice with a survey, you'd have these questions: Are you drug addicted? Are you a veteran? Are you this? Are you that? And then just record that information and just assign the membership to the overlap section. And so here, if we could have two-way overlaps, or let's say we could have as many as four-way overlaps, because you could certainly be a veteran, family, drug addicted, and aged out foster kid, then mathematically how you'd model that would be differently. But then you would just choose, okay, what cohorts do my samples belong to when I ground truth go out into the population and gather these samples? But you'd still want to spread out your samples. You might know that maybe they hang out at a particular soup kitchen, or maybe they stay certain times of the day in the library, or maybe roadway infrastructure, or shelters and things like that. So you would still take all of the locales that you know of where homeless congregate, and you would deploy your resources to each of those places without preference for one. But when you collect the data, you're going to have a different representation. I was simplifying it here just for the sake of explanation. Okay. Did I answer your question? Yeah. All right. Any other questions? No? All right. So we said that you don't know your population parameters, but you can use your estimators. You can deal with your estimators because you know what they are. You calculate them by measurement over the samples that you gather. And so this idea of stability is really, really important, unbiased and consistent, because if your estimator is stable, then you're guaranteed that whatever statement you make about this estimator will apply well to the population, keeping in mind that if your population distribution is very complex, you're going to have to gather a larger number of samples. Okay. Now, we talked about this idea of random variables as a vector. We talked about real world objects, I should say, as a vector of random variables that represents multiple measurements over these objects of interest that you gather as samples from the population. And we talked about the sample mean is a good estimator. It's stable for the population mean. And then we said this unbiased version of variance is a good estimator. It's stable and therefore good replacement for the population variance sigma squared. Any questions? No questions? All right. And so it's often been said that seeing is believing. And the visualization on these humans, I think what the neuroscientists say is about 90% of our brain matter is devoted to visual processing. So the visual sensory modality is really, really important. And in fact, when you have a data problem, one of the first things you need to do is look at it. And how you look at it is by visualizing it. And so you might try some visualization and then change your visualization and go through a series of iterations of stitching together data, transforming data, and selecting data and visualizing that data. That visualization stage is part of your analysis, and it helps guide the modeling decision in order to ultimately extract insights from your data. And so one of my favorite visualizations, and I just want to kind of show this as a way to demonstrate some of the power of these visualizations. This is what I like to call the pizza chart. Now, this pizza chart is for the continental US. It's geo-registered. And so for those of you in geography or thinking about geography, GIS types of problems are very, very important because oftentimes the usage of a lot of data science, not a lot, some data science, a big consumer, that's the word I'm looking for data science, are urban planning, farm management, all sorts of things that involve geographical constructs. And so here we have the continental US, and I don't remember what landmass, whether it's a county or what have you, represents each one of these blocks, but we have represented as a number of national pizza chains. Some of them I'm not very familiar with. Some of them I only know from rest stops. But nonetheless, we have Chuck E. Cheese, CC's Pizza, Domino's, Godfather's, Little Caesars, Papa John's, Papa Murphy's, Pizza Hut, and Sbarro. I think that I said that right. And so here in the continental US, one of the things that will really jump out at you, at least me, when I look at this, in this area in Nevada, there's a big pizza hole. There's like no pizza as far as these large national chains are concerned. Now, these are large chains. These aren't family, individually owned mom and pop types of pizza places. But nonetheless, when um, franchises and companies decide to place various store locations, they do a large demographic study about the population in that area. If you are a fan of dollar stores, I'm a fan of dollar stores, you'll notice the same company owns Family Dollar and Dollar General. And I can't remember which one, but the difference between the two has to do with the socioeconomic strata of the population within a certain radius of those stores. It's the same ownership, but they sell in to different types of profiles for disposable income and non-disposable income. So that being the case, I see that there's a big pizza hole here in Nevada. And then along the Northeast corridor from Boston to DC, we see a lot of Sbarro, and that's usually along Route 95, but we also see a lot of Domino's, right? Now, the Northeast corridor draws its name from Amtrak, and it's part of the most populous area of the United States. But in California here, along the coast, we see a lot of Papa Murphy's. And so they've made demographic decisions about where to locate these pizza franchises for these national companies based on lots of measurements, which they won't tell you. You have to be on the data science team for those companies, but you can kind of piece it together a little bit here and there from observation. Now, in this chart, we have franchise data, and they do their studies and they make their decisions about where to place these franchises based on demographic information, as well as dietary habits for members of the population. Now, you can take this data and you can combine it with something else and get all sorts of, or try to infer all sorts of things about customer behavior. For example, in this next chart, this is the population chart registered as a relief map. And so the higher the population, the higher the elevation registered here for each one of these points on the map. So here, the highest point, that's New York City, which is the most populous city in the country. And you'll see over here, we have Los Angeles, which is pretty high. And then we see Chicago, which is out here, which is another of the top, I think, 4 or 5 or 6 most populous cities, metros in the United States. And then Philadelphia over here is the 5th largest city in the United States. And so if you were to kind of flip back and forth between the pizza map and the population map, it kind of almost looks like you see dominoes where you have a lot of large urban areas, right? Because Domino's, they started their business, they're mostly or all delivery. You can certainly walk into a Domino's, but they seem to look at you weird when you do that, I found personally. But nonetheless, you can take this information and multiple sources of information and make statements beyond what you otherwise would have with just a singular data source. And so this idea of hidden linkages or hidden associations between measurements, here we have population, and here we have a categorical variable, most popular pizza vendor, from national chains. And you can put the two measurements together and notice that there's some coincidence between the two measures. Well, as population increase, the selection is different for the pizza brand. All right. And in fact, my wife and I, when we move, we have what we call the Trader Joe's test, right? We use Trader Joe's locations within a certain radius, 20 miles, to decide where we're going to look for a place to live. But anyways, any questions about this? So this is just to say, what does population have to do with pizza selection? Okay, well, there is an association there, and this is just one example of an association that's not as obvious as oil price and gasoline price. And so this idea of calculating these linkages and visualizing your data is really, really important, because at the end of the day, it guides your selection or modeling choice of what you're going to use to extract insights from your data. Any questions? No? And the URLs are there if you want to play with it. It's kind of interesting to tinker with. And so one of the chart types we're going to talk about a so-called bar chart, when you produce a histogram, that's nothing more than a bar chart. A histogram is a specific type of bar chart. The bar chart is more general than a histogram. It draws its name from the bars that you see, and a bar chart is typically used to visualize information about categorical variables. And here, along the horizontal axis, we see the season, and along the vertical axis, we see natural number counts. And this particular bar chart has to do with the number of children and born during various seasons for a particular family. Now, why someone would want to do this, I have no idea, but the chart was free, and I don't want to pay anymore for artwork and other stuff. But that being said, in the legend, you see that the largest number of children were born to this family in the summer and in the fall. And it looks like they have 5 children in total. And so when you articulate what your charts are, it's really important to help your audience understand what the chart means, because your audience has a finite attention span, and you want to shape or direct that attention span to the message that you're trying to get across. Okay, any questions? No? All right. So another reason why I said a bar chart is more general than a histogram, when you have a categorical variable, by its very definition, there's no natural ordering. And so in this chart, we have companies, various large companies, the largest employers in the United States, and we've chosen to organize or sort these particular categories along the horizontal axis in non-increasing order from the largest US employer to the smallest US employer. And so with a bar chart in general, because the horizontal axis is a category, it doesn't matter what order you have them in. That's different from the histogram, right? Because in the histogram, we have this idea of bins, and these bins have a particular ordering associated with them. And so here we see that Walmart stores is the largest employer, and along the vertical axis, we have counts representing the number of employees, and on the horizontal axis, we have the largest employers in the US, at least at the time when this was taken in 2013. And this is from USA Today. And so here we see that Walmart is much, much larger than the other employers, at least at that snapshot in time. And here, larger, higher means larger employer, lower means a smaller employer. And so certainly this changes, and you could actually register this bar chart in time and show from 2013, for example, to 2021, how these employee counts grew or shrunk over these years. Okay, any questions about this? Does that make sense? And so bar chart is available in Matplotlib, PyPlot more specifically, but histogram is a specific type of bar chart where the order does matter on the horizontal axis, because those are the bins representing the ranges of values for which you're doing your accounting. Any questions? Does that make sense? Yeah? Okay. And so here, we've taken the same bar chart for the Jones family, and we've taken each one of the bin counts on the vertical axis, and we've divided it or normalized it, so to speak, by the total number of samples. And when you do that, that is exactly a probability distribution. Each one of the bin values then becomes a relative frequency, and you can treat that relative frequency as a probability. And so one of the techniques you can use to estimate a probability is to take your counts, your histogram, divide the bin counts, individual bin counts, by the total number of samples, and use those proportions, those frequencies, directly as probabilities. Any questions about this? No, make sense? Okay, so you can transform your bar charts into something that almost looks like a histogram. Now, in this case, this particular histogram, the horizontal axis, they're categorical variables. And so it says spring, summer, fall, winter, but you could have very easily arranged it in all sorts of sorted orders. But if you have a histogram over something that's numerical, it's really important to have those bin ranges arranged in non-decreasing order. Okay, any questions? Does that make sense? No? All right. And so this is a pie chart. A pie chart is very useful for representing relative proportions, just like this histogram, but it's really good about part-whole relationships. This particular pie chart has to do with the amount or percentage of time that college students, I don't know how true this is, maybe it was true back in 2014, but it has to do with the proportion of time that college students spend on various activities. Now, of course, sleeping, I'm not sure who gets 8.7 hours of sleep anymore. Maybe more, maybe less. Okay, go figure. But it's really easy to see, for example, sleep, 8.7 hours, and the relative proportion that represents to the 24 hours over the course of the day. All right, any questions about this? And in pie plot, of course, you can do pie charts, and certainly you can associate labels with the different variable counts and things like that. All right. No questions? Any questions? No? All right. This next one, I think, is particularly important, a so-called scatter plot. And a scatter plot in 2 dimensions, as is depicted here, represents the outcome of multivariate measurements. And so in this particular case, we have 2 axes, the horizontal axis, x-axis, and the vertical axis, y-axis. Each one of those axes represents a random variable, and the tick marks along each of these axes represents the outcomes possible for those random variables. So if you have a bivariate random vector consisting of random variable x and random variable y, each outcome co-occurring xy is going to be registered as a coordinate. So here we have a value of x, that's 3, and a value of y, that's 5. And so the scatter plot doesn't represent time at all. It represents all of those co-occurrences, namely the instantiations of the random vectors. Now, one thing that you can do, we've represented here a random bivariate vector, 2 random variables. We can certainly represent 3. It would just be in 3 dimensions. Now, certainly beyond 3 dimensions, you can't visualize it. But in practice, when you visualize a scatter plot, you're going to do it 2 or 3 variables at a time. You might have a data problem that has 100 variables. So it's a 100 vector, and each instantiation represents a tuple of 100 different measurement outcomes. Now, in that case, what your enterprise to do is to examine relationships 2 to 3 variables at a time, and then based on those relationships, you let that guide what your modeling choices are. And we'll talk about considerations associated with how you choose those 2 or 3 variables at a time. But nonetheless, one thing that we can use, and this is an example of a scatter plot, along the horizontal axis, we have head coach salary in dollars, and yes, it gets pretty high, almost $8 million. And along the vertical axis, we have a rank of college football teams. Now, I'm not here to debate the merits of whether college football team head coaches should be paid a lot or paid little. That's not the purpose of this class. But what I will show you is that you'll notice in this scatter plot, of course, each point here, it's about $2 million, and the rank is about 50 for that particular college football team. Now, on the vertical axis, we have rank. So here, lower means better, right? The strongest team, most highly ranked team, would correspond to a value on the vertical axis that's closer to 0. And so one of the things that we notice here, that these points, they kind of form a cigar or a cloud. And this cloud looks like a cigar, and it's oriented pointing downward. That expresses a relationship that effectively says, as the head coach salary increases, in general, the rank gets better. Now, of course, perhaps it would have been better to have this thing sloping upwards. You'd have to transform the data, because when you say the best, it's kind of more visually pleasing for this best to be higher up. Question? And so here, when I say the shape of the cigar, we see a bunch of points, cigar, football, cloud, and you can imagine drawing an ellipse around it. And, it's like a cigar. And if it's more elongated, it's more eccentric as an ellipse. If it's kind of closer to being circular, it's less eccentric. But nonetheless, if you draw axes for the principal axis, giving you the direction for this point cloud, this ellipse, it's sloping downward. So that's what I mean by the cigar shape is pointing downward. Okay. Any other questions? No? All right. And so we notice this, and one of the things we can do is fit a line to this, a regression line, that is sort of in the middle of the data, and we'll talk more formally about how you compute that. But one of the things that this line does, because we know the equation of a line, y equals mx plus b, that m part, the slope, tells us what that relationship is between the horizontal axis variable and the vertical axis variable. In this case, the slope is negative, and it's fairly steep. And that slope is the relationship, linear relationship, between that variable for salary and that variable for football team rank. Does that make sense? Any questions about this? And we'll talk about the algorithm for fitting linear regression later on in the semester. Okay. And so another type of visualization we can have, a so-called line chart. And this particular chart is registered in time, and it's the closing price for security, namely Apple stock. So on the horizontal axis, we have a day, which is a reporting period, and the trading window for securities in the US, and I'm not talking about after hours trading, is Monday through Friday from, I think it's 9 a.m., 9:30, I think 9:30 to 4 p.m. I can't remember the open. I think it's 9:30. But nonetheless, the closing price represents the share price at the end of the trading day at 4 p.m. And so here in time, we plot horizontal axis is that trading day. And if you have a trading day on a Friday, the next trading day is the following Monday, and business days. If you have a holiday, that's a federal holiday, there's no trading on federal holidays. So that being the case, on the horizontal axis, we have the trading day, and it's a type of scatter plot. And on the vertical axis, we have the share price in US dollars. Now, it's also a practice in the financial community not to give you the dollar amount. Sometimes they use logarithm because it looks nicer, right? When you have a lot of measurements. But this is actual dollar amount. And so what makes the scatter plot a line plot, it's registered in time, and then we connect each subsequent point from an earlier date to the next date in time. And so on the bottom here, we have a line plot. And the idea here with the line plot is that there's a linear change in the share price throughout the course of the day. Now, if you were to take the measurement of the share price every 15 seconds, it doesn't do that. It jumps up and jumps down, and it's very, very chaotic in practice. But what this does afford you is this idea of trends over longer periods of time, not 15 seconds, days, weeks, months. What is the general direction, up or down or neutral, that this share price behaves, or how this measurement behaves? Any questions? Does that make sense? Okay. And so for things in time, it's often very useful to visualize these variables, these measurements in time, as a line chart. So for example, if it were heart rate, right? Blood pressure, things like that. How does it change per minute, per hour, per day, or seasonally throughout the year? And so we can then take this line chart, and just like we did with the other scatter plot for head coach salaries versus football team rankings, we can fit a line, a best fit line, choose a line, mx plus b, that's in the middle of the data, right? And so that's this red line here. So what it says is over this reporting period from March 2015 to March 2016, Apple stock went down. So if you were gambling or making an investing decision, I shouldn't say gambling, it's kind of gambling, then if you notice that Apple stock is going down, 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 you could use this information and make a decision. Well, I think it's undervalued, and I think it's going to go up, right? And do well for yourself in that way. Any questions about this? Does that make sense? So much so is this idea of gross level behavior over time. In the finance community, they look for certain patterns in these temporal graphs for these best fit lines. Some of the things they look for is they look for V shapes, they look for W's, they look for U shapes, they look for all sorts of pathologies in the graphs over various time scales, and use that to trigger automatic trades and automate their investment decisions. Okay, any questions? Does that make sense? All right. And so another thing that line charts are very good for is it allows you to make multiple comparisons between different categories of measurements. In this graph, we have along the horizontal axis, we have time, and along the vertical axis, we have temperature in degrees Fahrenheit. So higher means warmer. Now, the red graph is the measurement of temperature in Tianshui, China. Blue is Pueblo, Colorado, USA, and green is Asuncion, Paraguay. Now, one of the things you'll notice here right away is that Tianshui and Pueblo kind of look more similar to one another, whereas Asuncion, it's different. So what this represents here, you'll notice May, June, July in Asuncion, the temperature goes down, whereas in Tianshui and Pueblo, the temperature goes up. Well, if you look at the geography in Paraguay, that's kind of more at the equator, south of the equator. Yeah, south of the equator. So their winter coincides with our summer. And let's say you were growing a crop like coffee or something like that, and you know what your profile is in Pueblo or some crop in Pueblo. I don't think they grow coffee in Pueblo. Um, you might decide, I want to globalize my production. So I want to find another geography where I can grow coffee in the summer and harvest right as fall happens and do it that way. And so if I were in Pueblo growing coffee, I would choose Asuncion because their summer is during our winter and vice versa. Their winter is during our summer and vice versa. I might decide I want to plant something like apples. And therefore, I need a climate that is very similar to my climate in Pueblo. So I would choose Tianshui because their temperature profile more closely matches mine in Pueblo. And so these line plots, it's a type of scatter plot. Again, it's registered in time for the growing for the calendar year. And we have temperature being represented, the month and the temperature. And I can very quickly make a comparison between different measurements and talk about their similarities or their dissimilarities. Okay, any questions? No? Make sense? All right. Ooh, time goes fast. We have about 8 minutes. Okay. So variable couplings. Oftentimes, measurements move together or change together, what I've been calling variable couplings. If we look at this picture, for example, of apples, what it means to be an apple is different from what it means, for example, to be a pumpkin or a pineapple. They have a certain size, a certain color, hues of green, yellow, and red, a certain texture. Texture is a computer vision term, a variation of color over a space. And they have certain shapes, the kind of circular or maybe a mildly eccentric ellipse, not that stretched out. And so it's the unique combination of outcomes of measurements that defines what it means to be an apple versus a pumpkin. A pumpkin, it's a bigger size than an apple, okay? A pumpkin has orange and has a little bit of green. And so a pumpkin is an association of different values for size, shape, and texture than an apple. And so that means that measurements can vary together. And so let's define more formally a so-called joint distribution. We have our random vector, and in this case, I'm representing two random variables, but it can be an arbitrary rank, an arbitrary number of random variables. And so we have here a joint distribution, which is the probability associated with instantiations of random vectors of arbitrary rank. Now, with this distribution, we can certainly represent the distribution of a single variable or single measurement, the so-called marginal distribution within this random vector. And so here we talk about more formally what it means to say the probability of instantiation x, y, little y, for random variable big X, big Y. So P of xy is the probability that random variable big X, big Y takes on values little x, little y. Now, if you were to write it out kind of more expanded, that's like saying the probability that random variable big X takes on value little x, and at the same time, random variable big Y takes on value that should be little y. That's a typo. Big Y should be little y. All right, I'll correct that and repost it. And so here we have our instantiations of X and Y, and the events that we're concerned about are the collectively exhaustive, all the possible instantiations, little x and little y, that we can have for random variables, big X, big Y. And we need all of them collectively because that's what our probability is defined over. And therefore, if we were to add that up, it should equal to 1 in order to be a probability. Okay. Any questions about this? Does that make sense? Yeah. All right. And so here's an example to ground it out viscerally into things that we've done so far. Here is a probability distribution in table format. Along the horizontal axis, here, the columns, we have the outcomes of a coin flip, heads and tails. And along the vertical axis here, the rows for this probability table, we have the outcomes of a die roll. And so if I were to represent this as a random vector, we have C for the coin flip, and we have D for the die roll. And so here you'll see for each entry, we have heads and 1, we have tails and 1, and so forth. And each cell here in this 6x2 matrix, each cell represents an outcome for each of the instantiations of coin flip and die together. Okay. Any questions? And so if we were to calculate this, we have 1/2 for each outcome of a fair coin, and we have 1/6 for each outcome. I almost said eat outcome, all right, because I'm hungry. For each outcome of the die roll, we multiply them together, and we get 1/12 for the outcome of this co-occurrence for the die roll random variable and the coin flip random variable. And so if we add them all up, there are 12 cells. 1/12, 12 times, is 1. This is a proper probability. Any questions about this? Does that make sense? All right, we have about 3 minutes. And so one of the things we can do, so-called marginalization, is we can compute the so-called marginal distributions. When you have a random vector, you can absolutely calculate the probability of a single variable, but you have to acknowledge this idea that this outcome of a single variable co-occurs with outcomes of all the remaining variables. And this is the case for a 2-vector, a 3-vector, for a random vector of arbitrary dimension. And so mathematically here, if, for example, we wanted the probability of a particular outcome of the coin, well, for an outcome of heads, while the coin flip is heads, the die roll can be one of 6 choices. So we have to add all those up. And so we're summing down one of these columns, a so-called margin, and that's the operation called marginalization. In our summation here, we have the joint probability of outcome C and D. And then here we're summing over each instantiation of D. That's the summing down this particular column. And so we take 1/12, we add it together 6 many times, and we get 1/2. Same idea for the coin flip equals tails. Are there any questions? No? Does that make sense? All right. And so we'll end with this. We can also marginalize in the other direction across the rows. In that case, we have a particular outcome of a die roll, 1 through 6, and say for the 2 outcome, if we want to know what the probability of the 2 outcome is, if we're given this joint distribution, C and D, we have to sum across all the outcomes of the coin flip, because it's not enough to take the single variable. We have to account for the fact that these things co-occur. And so here for die roll outcome 2, we're going to sum die roll outcome 2 for coin flip heads and for coin flip tails. That's 1/12 plus 1/12, that's 2/12, which is 1/6. And so this marginalization works for arbitrary rank, but computationally, it gets very, very expensive. And there are shortcuts that we take algorithmically in order to approximate what the marginal is, because it takes a lot of computation to do this marginalization. If, for example, you had 10 or 20 or 100 variables in your random vector. Okay, any questions about this? Does that make sense? Yeah? All right. And so we're going to stop there. It's time. And we'll pick back up with the balance of this on Monday, along with the new material. Have a great weekend. Bundle up, stay warm, call your parents, tell them you're doing okay, you're not